you look for symmetry radially, 360 degrees around your central atom. So all of these guys are nonpolar. And then polar, there's just so many examples. Anything with an oxygen that is nonlinear. All the acids are polar. Anything that is non-symmetric, I'll draw the Lewis structure of ammonia. So those guys are polar. And then, adding on to that, the intermolecular forces, remember all molecules have London dispersion forces. So everybody here has London dispersion forces. And that's the weakest force. So if that's the only force they have, they're going to have the weakest intermolecular force, and they're going to have the lowest of all those things over there, solubility, boiling point, melting point, viscosity, surface tension, except for vapor pressure. And so I'll come back to that. So all molecules have London dispersion forces, LDF. And then polar molecules have dipole-dipole, but nonpolar don't. So polar molecules automatically have a higher boiling point, are more viscous, have higher surface tension, yada, 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 than nonpolar. Nonpolar are the losers. They're always at the bottom. And then, of course, hydrogen bonding is the strongest intermolecular force. Remember, we only need to know 3 of these: London dispersion, dipole-dipole, and hydrogen bonding. Hydrogen bonding are guys that have an OH, FH, or NH. So from what I've drawn here, this guy can hydrogen bond, and this guy can hydrogen bond. So they would have the highest boiling point, the highest melting point. They would be the most viscous. Okay, one more thing to tell you before we try the Kahoot. Oh, vapor pressure, vapor pressure. Let's draw. Let's do a little drawing. I think I've talked about what vapor pressure is already, but that doesn't mean that you remember. Okay, so you're at home, and you're trying to get water to boil. I don't know why I do the handle to my pot weird like that. This is a pot. What vapor pressure is it's the pressure that the liquid exerts against the atmosphere. And of course, the atmosphere has its own pressure. So the liquid, and I'm just choosing water here, it's pushing up against the atmosphere pressure. The atmosphere pressure is coming from just the atoms in the air, which we know is mostly nitrogen and oxygen. So that's vapor pressure. The pressure that the liquid exerts against the atmospheric pressure. They're fighting each other to get something to boil. So if a compound has a low vapor pressure, it's hard to get it to boil because it doesn't have a lot of force pushing up against the atmospheric pressure. So if it has a low vapor pressure, stay with me because there's 3 layers of understanding to understand vapor pressure. If it has a low vapor pressure, it's not fighting against the atmospheric pressure. It stays as a liquid more easily, and that's because it has really strong intermolecular forces and it's holding on to itself, and it doesn't want to become a gas and fight up against the atmospheric pressure. It would rather hang out with itself because it has really strong intermolecular forces. So low vapor pressure means strong intermolecular forces, IMF, intermolecular forces, which means it has a high boiling point. It takes a lot of heat to get it to separate because it's attracted to itself. So vapor pressure is the only one that is an opposite trend of everybody else. If something has a high melting point, high boiling point, high solubility, it has a low vapor pressure. So that one is opposite. And when vapor pressure overcomes atmospheric pressure, that's the definition of the boiling point, whatever temperature that happens at. And why is that temperature dependent? Because the more molecule, the more kinetic energy it has, the more motion it has, and eventually you turn it into a gas. Okay, that is a summary of what we talked, oh, one more thing. Remember, the larger the molecule, the larger the surface area, the more intermolecular forces it has. So look at the London dispersion with the colored balls down here. Iodine, I2, is a bigger guy than bromine, than chlorine. And so I2 is gonna have the highest boiling point because he's gonna have the strongest intermolecular forces because he has the biggest surface area. So let's look at a periodic table and review atomic size. So we can see why the hell does iodine have the largest boiling point of all the diatomics. So the larger the atom, the more surface area, the stronger the intermolecular forces, the higher the boiling point, the lower the vapor pressure. Remember, francium is the biggest boy and the weakest boy. He has the lowest electronegativity and he has the lowest ionization energy. And then we get smaller as we go towards fluorine. Fluorine is the smallest boy and he's the most angry. He has the highest electronegativity and the highest ionization energy. Those are the three trends you need to know for general chemistry. Okay, marinate on that while you get in. Oh, wait a minute. Wait a minute. One moment. There was a Christmas edition. Oh, whatever. Oh, here it is. Winter holiday. It's just a background, but you know we should do it anyway. All right, here we go. 10 points for the final. And then next week, we're going to review for the final both days. And again, you just need to show up to your discussion next week. You get 25 out of 25 points. And your TAs are going to review for the final as well. That is what they're going to do. Which is very good to hear different versions of explanations. So even though I'm going to review for the final, you definitely want to hear your TA's version. Because this is good to hear different explanations. Maybe you don't understand what I'm saying. You know what I'm saying? Maybe they say it in a way that you understand.
50. It's 56. It's 56.
Okay, so if you're not into this and you never win, doesn't matter. What you need to do is write down the answer choices. Because those are the ones that are going to be on the final, the exact same molecule. I'm not going to give you anything different. And I'm going to give you time to write down the answer choices.